All right, today we're going on a hunt. We're diving deep inside our own cells to find a master switch, a switch that tumors are secretly using to stay alive. This is basically a molecular detective story about how we might one day be able to starve cancer. So think about this for a second. Imagine a tumor isn't just one single bad guy, but it's more like a rogue city that's just expanding out of control. Now, for that city to survive, it needs roads, it needs power, it needs supplies. So what if the key isn't some big frontal assault? What if we could just lay siege to it and cut off its supply lines?
Because every rogue city, every tumor, has to have a lifeline to keep growing. And for a tumor, that lifeline is blood.
Now, that lifeline has a scientific name. It's called angiogenesis. It's the process our bodies use all the time to form new blood vessels, when we're healing from a cut. But tumors hijack this process. They literally trick our bodies into building a private, dedicated highway of blood vessels straight to them. This is the absolute critical step that lets a tumor get bigger, thrive, and eventually spread.
Okay, so let's zoom in even closer. If angiogenesis is the big picture project, building the highway system, the actual boots-on-the-ground work is done by something called endothelial cell sprouting. You can think of these guys as the construction crew. They're the cells lining our blood vessels, and they literally start to sprout and stretch out, forming new branches that become those new roads for the tumor. It's a very physical, very mechanical process.
So, if we want to stop this construction project, we've got to figure out what's driving the machinery. And that leads us to our first major clue, a protein that's right at the center of this whole puzzle.
Scientists already had a known accomplice in their sights, a protein called RhoJ. They knew it was present in really high levels in a tumor's blood vessels. And they'd already run experiments showing that if you mess with RhoJ, you can slow down tumor growth. So we know it's a key player, for sure. But the real question was, how does it get turned on in the first place? And you can literally see what it does. On one side, you have a normal, calm, smooth endothelial cell. But then, when RhoJ gets activated, the whole cell just transforms. It grows these wild, spidery arms. Those are the actual sprouts that start a new blood vessel. So RhoJ is clearly the engine, no doubt about it. But every engine needs a key to get started.
And this brings us right to the heart of the mystery. The researchers knew RhoJ was driving the getaway car, but they had no idea who was holding the keys. The hunt for that on switch was officially on.
This was the exact question they needed to answer. What flips the switch on RhoJ? Now, in cell biology, these switches are usually other specialized proteins called activators. The problem is, a single cell has dozens of them. So the challenge was finding the one specific activator that was responsible for this. So here's how they approached it, and it's pretty clever. They started with a really smart hypothesis. They knew RhoJ was a close cousin to another well-known protein. So they thought, hey, maybe its activator is also from the same family. And just like that, with one logical leap, they narrowed down a huge list of possibilities to just two prime suspects, intersectin 1 and its close relative, intersectin 2.
Okay, so now they had their suspects. The next step was to set up a sort of molecular lineup to see if either one of them was the real culprit. And what they found, well, it was a massive breakthrough.
This chart right here, this is the aha moment. It's the smoking gun. What you're seeing is the amount of active RhoJ in the cells. The first bar is the control, just a baseline level. Then they added intersectin 2, the second suspect, and nothing. Barely a change. But then, look what happens when they add intersectin 1. The activity level just skyrockets. It was a clear, undeniable signal they'd found their switch.
And you don't have to take my word for it. The researchers put it right there in their paper, stating it clearly. ITSN1 is the thing that turns on RhoJ, which then causes the sprouting. The detectives had found their culprit.
But in great science, just like in a great detective story, finding your main suspect isn't quite enough. You have to prove, beyond a shadow of a doubt, that they're the one who pulled the trigger. You have to make sure they acted directly. And to do that, the scientists came up with this incredibly slick experiment. They basically built a trap. They engineered a decoy version of the RhoJ protein. Now this decoy is broken. It can't cause any sprouting on its own. But, and this is the key part, it can still physically grab onto its activator, ITSN1. So the theory was, if ITSN1 is really the direct activator, this decoy should snatch it up and take it out of commission, stopping the whole process cold.
And the trap worked perfectly. When they just had the activator, ITSN1, the cells went crazy with sprouting. But the moment they added that RhoJ decoy, everything just stopped, dead in its tracks. The decoy latched onto ITSN1, proving there's a direct physical connection between them. Case closed.
But just when you think the story's all wrapped up, there's one final twist. Because it turns out this whole system isn't just a simple on switch. Nature's always a bit more elegant than that. The researchers discovered that the cell also has a built-in brake to keep everything under control.
And that brake is another protein, called FAK. Just look at what happens when FAK shows up. With ITSN all by itself, RhoJ activity is flying high. But add FAK to the mix, and it's like someone slammed on the brakes. RhoJ activation drops way down. So it's not just an on-off switch, it's a beautifully fine-tuned system with both an accelerator and a brake.
So, what's the #1 big takeaway here? It's that we now have this crystal clear chain of command that we never knew about before. We have a specific, proven pathway. ITSN1 flips the switch on RhoJ, and RhoJ drives angiogenesis. Pinpointing this exact line of dominoes, that's a huge leap forward.
And all this discovery leads us to one massive and really hopeful question. For years, the goal has been to stop angiogenesis. Now that scientists have found the specific key that turns the engine, ITSN1, can they start designing an off button? Can they build a drug that specifically blocks that key so it can never start the engine in the first place? It gives us a brand new, incredibly promising target in the ongoing fight to starve cancer.